Hi. Can you hear me? Hi. Now, some announcement first. I guess probably you know I announced already. Next Wednesday we don't have class. Because we will schedule that for the purpose of a optional class for the Art Studio. And second thing is homework 3 has been there. Okay, so you have like 2 weeks to do it. So after today, probably you are able to finish it because there are only a few things that we cover today. Then we will be done with that. Okay. And first thing is we have uploaded last year paper, so you may want to take a look. We won't give the written solution to that, but we will discuss it at the end of the course. Okay, so before the test, the last class, we will discuss that. Okay, so this is the first thing. What else I need to announce? Let's see. Yeah, probably that's it. Is there a question before we start? Yeah, the test is 1 hour. Will be in YILT5. It's open book, but not open notes. Open book notes, but not open your iPad or notebook. So you bring whatever you need, and make sure that you bring your calculator. Okay, because you are not allowed to use a smartphone as a calculator. And I will not provide any table. You bring your own. And then make sure you have your student ID to check, to make sure that you're the one who takes the exam. So if you cannot take the exam, let us know. If you have valid reason, we will allow you to take the makeup. But in most cases, there shouldn't be a makeup unless you have a valid reason for the absence. Okay. Gonna make it started. So the goal today is to finish the estimation part, and we will talk a little bit about hypothesis testing. So estimation, let's finish that part. So estimation, I will just quickly review more than a little bit more detail, because as you will see, the idea behind estimation and hypothesis testing is so similar that you probably would think that they are basically the two sides of the same coin. Okay, and let me finish this. I will talk about why they are very close to each other. But first, let me recall the definition we said, right? Just to make sure that you understand so we have the population parameter. Okay, population, you can imagine, consists of, say, many people, well, many people. They have say income or age or many numbers, right? You can describe, and usually we don't care about the data per se because we are unable to collect them anyway. So we care about how to summarize them, right? So it's care about the summary statistics, like mean variance, and that usually is the parameter we try to guess. Okay, remember the example is suppose you work for Elon Musk, who are thinking to introduce a smartphone to China. where his smartphone is able to talk to a satellite. The question is probably you want to know what the income of 1.4 billion people, right? That is something you care. And you want to know the mean, right? And the variance as well. And how are you going to get them, right? Unless you ask for 1.4 billion, you are unable to get it anyway. So the way to do it is have an educated guess. And the way to guess is called estimator, right? Estimator is a systematic way to guess, right? Based on the data you got, okay? And since the data we learn is a random variable, the rule you guess is also a random variable, okay? And the way to guess mean, as we argue, is the sample mean, right? As the name suggests already. Usually we denote it as a theta hat, and there's a n is denoted as is the dependence on n, right? Because it is changing based on the sample size, right? The sample mean is divided by n, right? And sample variance as the way later as we argue, right? We argue that is the way to estimate population variance. Okay, and for sample mean, you probably will see the parallel between the calculation formula of population mean and sample mean. That is a coincidence. In general, the way you calculate estimator is different from the way you calculate the population parameter, right? And as we see, the sample variance is n over n minus 1 rather over n, right? We'll talk about that later, but just terminology, estimate is the number, and estimator is a rule. So estimate is a number, and estimate is a function of a random variable, and estimate is particular number. So there's no more random variable there. Okay, it's just a number. And there are two types of estimator. One is called the point, the other is called interval. And as you can see, point is just you just give one thing, and interval is more than one, right? And the thing that you saw on the TV, the analysts, they would say just a number that's point estimate. If they say more than one, then it's interval, right? Often they give the lower bound, upper bound. Okay, so that is the way we do. So point estimate, and there are three good property, and we will try to argue that sample mean satisfy three of them, and sample variance, the way we see satisfy unbiasedness. I will not talk about efficiency and consistency related to the sample variance because that's out of the scope. So unbiasedness actually mean, let me repeat again, is if you have many sample, but do note that we will just only do one, right, in general. But suppose we're able to repeat ourselves to have many sample, and for each sample we use our estimator theta hat n, right? We come up with many estimate, and average of those estimate, right? That's what expectation means. Right? Average of those estimate is actually the what we're gonna guess, right? So what it means is, suppose I have many sample. Each sample I have the sample mean. Average of this sample mean will be the population mean. If that's the case, that's called unbiased. And similarly, if I have many sample, each sample I have the sample variance, okay? And average of those sample variances is the population variance, then it is unbiased. And that explains why we need to divide it by n minus 1 instead of n, because if you divide by n, you miss the target, okay? This is a graphical illustration again, is the average of these three numbers end up in the middle. So that is the meaning of the unbiasedness. And efficiency means how accurate or how good is our estimator. And we learned that unbiased on average hitting the target, and if on general you're closer to the target, that's better. That's called more efficient. That is, compare A and B. A is closer compared to B. That is what it means by efficiency. And the last one is consistency. That is considering the case we have a very, very big sample. Okay. Suppose we have increasing, the sample is making sample size getting larger and larger and larger and larger. If what we are trying to guess, right, the rule we use is so close and close and close such that there would be no more uncertainty, right? And that's consistent, right? So it's a hypothetical case where you get so many samples and we get what we want, then it's called consistent, okay? And just remind you, this is the case. Need not be unbiased, right? When you have sample size of 1 is outside, 2 is inside, 3 is getting closer. It doesn't mean as unbiased, but at the end of the day, even though it's biased, but it's so close that you don't really worry about it. Okay. So consistency is independent of unbiasedness idea. Okay. It simply means that the sample size gets bigger and bigger and bigger and bigger and bigger. Okay. You use your estimator to guess what it is. There's no difference between almost what you get is what you want. Okay. That's what you try to get is what you want. Okay. There may be some distribution, but it's so close that, I mean, the n get bigger, there would be no difference for whatever number you try to get. Okay. So this is guaranteed by law of large number, right? Sample mean, just simply this thing is good, and we have argued that the sample variance is like this. Okay, some of you may still puzzle that why we have to divide by n-1 instead of n. One of the reasons, actually, I write that in the slide, is because we have to estimate x bar. Suppose we, instead of x bar, we have mu there. Okay. If we have mu there, then we don't have problem. We can just divide by n. But because of the fact that we need to figure what's x bar, okay, so there's a problem. Okay. For this claim, you can check the proof. If you know the mu, so x bar, then you don't have an issue. Now, next is talk about the special case of binary data. Later you will see today why we focus on this, because there's some formula that make it easier, and also some common way to handle those things. And binary data, just basically data are 0 or 1, right? Whether you like curry food, whether you are boy or girl, okay. Very simple data. And the thing we care when the 0, 1 is the proportion, right? The example would be, maybe I want to care what is the gender ratio in CHK, right? How many boys relative to girl, right? Or percentage of girl in the school, right? I conjecture that I think it's like 70% of the student are female, right? And that would be the pi. Okay. And but probably want to make a guess, right? And look at how many boys and girls here. I think roughly the same, right? In that case, p is at half, right? Because I look at people here, right? Boy will get 0. I mean, the girl, that would be 1, so on and so forth, right? Average of this, right? Adding 0 and 1 and over n, that was the proportion. Okay, so that's we call p. And for binary data, the variance is very simple. It's just pi times 1 minus pi. Okay, don't note that this is a population. I mean, okay. And the way we guess the variance is just simply because pi is just p, so we just use this. Okay. So There are many reasons why we use this, but turn out that this is bias estimate. Although this is biased, but we still use it because of the unbiased version. Is not a big deal because n in this case usually is very big. So you don't need to worry about this part because this is big, so it's not a problem. So this is it. Then you just have the formula there. Now next is interval estimator, okay? And I will tell you that this is very closely related to hypothesis testing. We'll talk about that in the second half of this class, okay? So I hope you pay attention, but I'll go for the example again because this is the thing you need to do for assignment, for your final test, and possibly for your project as well. So the idea is that we focus on what we call interval estimate for the mean, okay, the population mean. We want to get a guess. The guess is, we know the sample mean is a good estimator. We argued it many times already. The question is, we are not satisfied with just one number. Okay? We want to have a better than one thing. We want to have an interval estimate. The idea of interval estimate is that I want to say for X bar, I go up by M, go down by M, interval, right? Set at M, right? An interval such that I have high probability to include mu, okay? So the idea is, let me draw down again to say a few things, okay? So the idea is, we know X bar in this very good, okay? The idea is I want to go right by M, symmetrically by M, right? That is X bar plus M and X bar minus M, okay? I want this, okay, to have high probability to include the population mean, okay? That's the overreaching goal, okay? High probability to include our population mean, right? Because we want to guess this, okay? I don't want to just get this number, right? Guessing this number doesn't tell me how likely the other value are, right? So I want to have better. How can I achieve this? Okay. The main idea is rely on the fact that X bar follow a bell curve by central limit theorem. Okay. Or if you make normality assumption. So let's draw again because it's so important that it worth talk again. So central limit theorem and unbiasedness tell us that X bar is a bell curve the p mu, right? And X bar n, right? Then the variance, right, of X bar n, we know it is sigma square over n. We learned that from last topic already. Okay. So the idea is that mu, right? If we know this guy, right? So we know that how likely that X bar is fall within this region, right? Suppose I want this area to be 1 minus alpha, where alpha is a very small number, right? And if I want this area to be symmetric about mu, right? That means that this area is alpha over 2. This area is alpha over 2, right? And this is a bell. If you want to know this area, this location, right? The way to do it is you can transform this to the case where I have Z here, right? And I have 0 in the middle, right? if I want this to be 1 minus alpha, right? And I want this guy to be alpha over 2, right? This guy, right? The way we denote is called Z alpha over 2, right? Because the way we denote is the right tail area, right? Or, right, the way this is equivalent to saying f of Z alpha over 2. There's a number there, right, equal to 1 minus alpha over 2, right? So because look at the left-hand side area, right? F of this number is equal to 1 minus, right? Or this is basically look at the Z table, look at where is the number there, okay? And that imply this number is mu plus Z alpha over 2 sigma over root n, right? Because that's how you transform between the standard normal and the normal bell, right? It's just u plus this times SD, right? Because this is asking how many SD from the mean, right? So that's ID. And now the magic happens here, okay? We know X bar, right, is very likely to be between this, right? Highly likely, okay? But what we want is the opposite case, right? We want X bar very likely to include mu, right? So let's make it clear. So what we know from the central theorem is how likely X bar is fall within the M distance, right? So this is we call M, right? Right. So the magic is like this, right? I take the M, right? But remember, large chance we are here, X bar, right? We have 1 alpha, probably 1 alpha is within this region, right? And the way that we go extend X bar by M, left and right, right? And as long as X bar is within this region, you do this procedure, go left by M, go right by M, it would include mu, right? Let me repeat the statement. X bar is very likely to be here, right? And if whenever you get X bar, you go left by M, go right by M, right? For sure you include mu, right? So this is the way that why this works, right? Look at the graph, right? So that's why we have the confidence interval is X bar plus minus M, right? M is this guy, right? Because most likely is fall within this, right? And we extend by this distance, right? Within, as long as X bar is here, which is very likely, right? Highly likely, one with probably 1 minus alpha, we do the procedure, extend left and right by M, then we're done. Okay, so that is the trick behind. Of course, you probably won't be able to reproduce this trick, but I hope that I convey the message why this is true. But of course, for all the purpose of exam or assignment, right? The thing you need is to, this is the formula that you apply, right? There's nothing very deep there, okay? And we'll have the similar idea when we do hypothesis testing. So do remind yourself, this is the graph that we'll be using again. So this example, I'm not going line by line again, but this is just X bar plus minus Z alpha 2 sigma over root n. Okay, and x bar is 3. You just put in here, right? And n is 64. It's coupled here, right? Sigma is this guy, and this guy is 95, right? So the idea is the center is 95, right? So both sides 5%, right? Add together 5%. So this is 2.5, right? The other 2.5. And that means that all the area on the left is 97.5, right? So, or this is 2.5, right? Or 0.025. Okay? And in Excel, you just do norm S inward. Area on the left is 90.975. Okay. So because alpha is 95. Okay. Is that okay? Is that okay? That's how we do that. Okay. Do note that the C alpha over 2 is asking the right tail area. Okay. So that's the notation we use. And many other textbooks also use the same notation. So not my invention. Okay. And if you don't know the S, sorry, sigma, you need to use S, okay? But that's no problem, as long as we're willing to make the assumption that the underlying distribution is normal, okay? In the assumption that we make, it's just like assume the income of China, if you work for Elon Musk, the case is Bell, okay? If you're willing to make the assumption, which might or might not be true, you can use the T distribution. So this is the formula, right? The only difference are two things. First is we don't know sigma, so we use S to replace, right? So it is before sigma. Second, this one, right? Before is Z alpha over 2, right? But now we have this one, right? So for an Excel formula, will be just T inward, right? 1 over alpha over 2, and then n minus 1. Right? So that is the formula that you use. Okay. And no, so this is the way that you handle it. Just the same question, but you just replace it by the stuff that we mentioned, right? It's just the formula there. Okay. Not going to go line by line again because I don't think we need to. Okay. So the next is binary data. Okay. Binary data, there's no different from the formula we have. Okay. The only difference is we don't need to worry about sample variance. Okay. Because for binary data, sample mean and sample variance are closely related, right? Because one is P times 1 is P. Right? So once you know the mean, I know the variance. So that's why we don't need to worry about that, and we can use Z always. Okay. That is the idea. Okay. And for this to work, make sure that this must be holding. For this to be an good approximation. Okay. Because in general, this is not normal, right? But it's okay to use normal to do it if this satisfies. Now, this we do example again because I think that will be it's not too, we do not need too much time on that one. So this common interval for sample proportion with N64 sample proportion is 0.25, okay? So in that case, we're done because if I want to guess, it's a point estimate, right? Suppose this is the question I asked 64 people, how many of them like spicy food, okay? And a quarter of them like spicy food, and that will be my best guess if I just want to do point estimate, okay? And then I'm done, okay? But now if I go to do it, right, I want to give an interval estimate, right? The formula will be like this, right? P plus minus Z alpha over 2 square root P 1 minus P over N. So that is the formula, okay? And you can easily see that P is already there, right? Coming from there, right? P is also here, P is also here. So almost done. N is almost done as well, right? N is 64 here, right? So what's left is this guy, right? And very luckily, we are looking at 95% confidence, right? So just to remind you, right, how to 95. Here is 0.95, right? And this is 0.025. This is 0.025, right? That means that this guy is 0.975, okay? And you can use the Z table, right? Look at where the entry are 1.96, then go back to the row and column and figure that out. Or you can use Excel, which is more common. Right? You can do norm doc S inverse 0.975. Okay? Please convince yourself how you're able to look for that in your set table, because you don't have Excel when you have the test. Okay? Make sure that you know how to operate the set table. Okay? If you make sure that you also remember to bring your own set table, right? You can bring as many as you want. Okay? I'm not going to print that out. Okay? Is that okay? Is that clear? So we will end this section by looking at something that related to sample size. Okay? That actually help you to do your project if you try to do survey. Right? For those who haven't think about your project, should take some time to do it, because you need to write 2 pages, right? I think, right? 1 or 2 pages for your project, right? If you have more than 2 people, then you just multiply by the group size. So it's an open-ended assignment, but it shouldn't be too much difficult, okay? Because I already showed you how your previous cohort have done that. It's not something terribly complicated. Okay, sample size. So the idea, what we want is, remember the overarching goal of this topic is to try to guess, okay? And use the data to help us to know what happened, okay? And the question would be, can we thought about the number of sample size we need to collect before we do it, right? And of course, you will think, okay, why don't I just collect one data, one sample point? Is it enough? No. Collect more? Not enough. More and more and more, right? You can keep doing that, right? That's fine. We can keep changing our sample size, okay? That is sometimes we do in this way. But if you go to business world, right? The boss asks you, when can you get me the answer? Okay? You say, oh, it depends. Let me see if I'm done and I'm done. And then boss said, you're done, okay? Right? You have to tell them when you're done and what's the budget for doing that, right? And that's the idea, okay? I will give an idea that when you'll be okay, okay? If for point estimate, you don't have problem, right? Because whatever you get, you just tell your boss, right? The problem is interval estimate, okay? The interval estimate, right, will depends on the sample, the variance you got, right? And the variance is inverse with the n, right? The bigger the n is likely, then the interval is getting smaller. So you need to tell me how accurate you want, okay? Which your boss tell you how accurate they want. Then you can tell your boss how big the sample size is, right? So remember we have just done, right? When we do interval estimate, this is the margin of error, okay? We focus on the case where only sigma is known, okay? We don't do the t thing, but idea is very similar, but we just focus on the normal case, okay? So this is the formula, okay? This is the how you go by left and right by m. Is how precise is your prediction, okay? And the way to know the n is very simple. You just make n a subject, right? So the way to do, you multiply both sides by root n, right? And using the high school math method that cancel out. Okay. And the next step is you then divide both sides by ME, right? And by high school math, this is gone. And what left is root n equal to that, okay? And using high school math again, you take square on both sides, right? Then that's the answer, okay? What is only little bit tricky is I have what we call the ceiling function. The reason is the sample size is usually integer. So if you get 14.1, then you get 15, right? You get 19.5, you get 20, right? Just the smallest integer, right? That is just bigger than this number. Okay? Let me show example. It's not complicated because this is the formula they apply, right? There's nothing deep there. Okay. The only thing is probably the difficult part is to get the ME, but usually the boss will tell you, right? So you don't have to worry about this part. Or is what do you want once we get the estimate, how accurate you want. Okay. And here you notice we don't need to know any knowledge about mu, right? Because the mu is something we're going to guess. We just need to know the sigma square. Okay. That's the only thing. And probably some of you would worry about how can we get sigma square. Okay. The idea is not that difficult. They're a good guess of sigma square. Remember, we talk about under normal assumption, right? And we learned that under normal, right? 99% of data will be within 3 standard deviation, right? So that means that the smallest number and biggest number, usually the distance is 6 standard deviation, right? So if you know the smallest, the biggest, which is usually easy to guess, you divide by 6, then will be the good guess for the sigma. So that's being adopted. I illustrate that in the next example. That's how I get the number 10. So this example that I use, okay, I assume the population of normal distribution standard deviation 10. How I get that? What I'm doing there? I didn't write it down, but this is I'm looking at IQ. So we know IQ generically is like 100. Okay, some idea, but anyway, we want to know, right? Because probably we know Hong Kong is the place I think is second highest IQ in the world with the average 108. But anyway, how to get that number. But anyway, how I get the standard deviation of 10. Okay. Genetically, IQ can be as low as 0, can be as high as many high, but usually the lowest low you can get is like 70, right? The high you can get is like 130, right? So the distance is like 60, right? Divide by 6, 10. That's how I get this 10. Okay. But there are many ways to estimate standard deviation as a crew gauge. There's no problem to get a larger standard deviation. Even they say, hey, you may get 10, you get 15, it's no problem. You get a wrong guess, you just get a larger sample size. There's no problem. Okay. You can make a larger overestimation or issue there. Okay. Now, what we want is, suppose I want to get the average IQ in Hong Kong with the margin of error is 4, right? Of course, you want to maybe getting smaller and smaller, right? Suppose I'm okay, I'm happy to have the sample mean, say 108 is between 104 and 112 is fine. If that's fine with me, then what I need is 25. Okay? How to get this? Apply the formula, right? Because this formula is just this, just to recall. I'll check back the last line. And just Z R over 2 square, and then sigma square over ME. Okay. And this is like 2, right? It's 4, right? And this is just 10 square 100, right? 100 times, so 400 over 60, that is 25. Okay. So if I just need, I'm happy to have 4 margin of error, I only 35, right? And what happens if I want ME equal to 2, right? And if I want to half of my ME, look at the denominator square. So actually I need 4 times as much data. I need 100. Can you see that? Okay. And if I want to margin error 1, right? Then I need how much? Right? I need 400. Right? So it's easy to see why when you ask more around 2,000 or 6, right? Or 1,600 to be exact, right? Then it's very accurate already, right? So that's why you can see people can do IQ around the world, right? You don't have to ask too many people, okay? And you do notice that this is independent of how many people in the population. We never have to think about there are 8 million people or 7 million people in Hong Kong. Nothing is being asked for that, right? So rather interesting case, right? Because of that, right? Actually, when we do market research, right? If you care, it doesn't really it doesn't make a big difference when you do that for China or do that in a small city in Hong Kong, right? As long as you think they share the same standard deviation, right? But of course, you might imagine if you have a different city, this standard deviation can be different, okay? That is hidden in that assumption, okay? Although I say it's independent of population, but this 10, okay, can be very different, right? I don't know if China, do they have a large variance or smaller variance in terms of IQ? I cannot conjecture that, I don't know. Maybe smaller, maybe bigger, right? Because bigger country, do they have bigger variance? I'm not sure. Whether smaller, bigger, it's not clear to me. But I think for the IQ thing, I think 10 is a good estimate. Okay? I don't see too much different for that. Now let me get to the very last thing. So I take a little bit time from the break, but that will be some consistency. So this is very simple. Now, instead of talking about some normal data, we focus on the data of binary data. And binary data, we no longer have the sigma, right? Sigma square is indeed pi times minus pi. Okay. So basically, this is the formula. Nothing new here, right? Just replace sigma square by pi times pi. There's nothing new. Okay. Okay. So the formula just apply directly. Okay. Which like this, right? Suppose I know what I think the population proportion is 0.4. How you get that? Come from previous survey, okay? And you want to do the survey again, okay? And that's how you get number, right? I'm not going to go to the calculation because it's exactly the same, okay? And but the question would be whether paradoxically, if I have good estimate of this, what am I doing? Right? If I have this already, why I'm doing survey again? Right? Or how can I get this number in general? Right? Suppose I want to ask, how many CHK students like spicy food? I don't have a good guess. Right? Right? And probably if you go to interview for investment bank, they will just make this interview question anyway, right? Try to get our way to get this, right? Some smart question. So how can we solve this problem? In general, we don't know. Okay. The way to do it, actually, people are very smart. The idea is to use the idea that pi times 1 minus pi at most is a quarter. And the maximum is 1/2. The idea is coming from the fact you learn from the high school that pi times 1 minus pi is a parabola. When pi is 0, this guy is 0, right? 0 times 1, 0. When pi is 1, this is also 0. 1 times 1 minus 1, this is 0. Okay? And you can easily see that positive number. Okay? And turn out that when it's 1/2, that's the maximum. Okay? And you can easily prove it if you remember how to do quadratic equation. Okay? So that is the maximum, 1/4. Of course, we are not math class. We don't ask you to do it. So this is the fact. We're going to stay. This is less than 1/4, right? So this is the fact. You can prove it. But we don't really care about the pi. We don't know. So we use the most conservative one, 1/4. So since many of you are from accounting, so using a conservative thing shouldn't be something that you have to think twice, right? Use the worst case scenario as our analysis. Okay. So the formula is nothing new, but we just the same. Instead of using the number there, we use 0.025. So this is a number, right? That we need. Okay. So you can see that if I want to ask for proportional data, and if I want it to be in precise 0.1, okay, which is still big, right? Because maybe I have the sample proportion is 0.6, right? the interval estimate will give me 0.5 and 0.7. But anyway, if we're able, we accept that, we only need to ask 100. Right? So the same idea, if I want to make my precision, say, like plus minus 0.05, how many we need? 400, right? And if I wanted to precise at plus minus, let me write down here, right? I want plus minus 0.0, plus minus 0.01, right? I need around 100, right? And I want plus minus 0.05, right? Then it's more like 400, right? And plus minus 0.025, right? And it's more like 1060, right? And you can see, maybe I go one step further, right? Right? If I continue to do that, right? Right? So you can see that's the reason, okay, why you look at the election poll around the world, whenever the election in UK, election in US, election in Canada, Australia, right? They often ask is around 2,000 people, right? Or 1,000 or up to 1,000 to 2,000, right? Or maybe 5,000, right? Why is the case? Why is the case no matter which country you look at? It's the same number, right? You may be wonder why. That's the reason, right? It's independent of how many population in the, how many people in the population, right? Or how many population in the population, but you know what I'm saying, right? Because the precision, if you want, is predetermined, right? We do know that we don't need to assume anything normal distribution, right? Because it's binary data, okay? So the assumption to make this work is very minimal, right? As long as you think your data collection is a random sample, okay? If that's the case, then everything works out nicely, okay? And what might be the case where you collect this, whether you support Donald Trump or not, you support that or not, right? You like curry food or not, it's whether you do the sample is the right way, right? And very often the problem is you do the telephone, right? And some people don't pick up telephone, or you do internet survey, right? You miss old people, right? And these are the problem rather than the methodology, right? If you get the right sample, everything is very accurate. Okay. I guess if there's no question, we're done with our estimation. Okay. After the break, we'll talk about hypothesis testing. So let me go for the you reply, so that you reply to me how fast and how slow I'm doing today. Okay. So let's have a break of 15 minutes. So we'll resume at 10:40. So I guess we can go to the comment to see how well you are, how fast I am, most importantly. Pi and P mean. When we have sample, when you have the focus on data, where it's binary data, right? Mu is simply pi. X bar is just P. Okay. Let me draw it to make sure that everybody get it. Okay. We have a population. Okay. Okay. We have many people here, right? And suppose we are interested in how much money they got, right? Then, right, maybe this money they got, right? And you care about the average with the mu, right? It's adding them up divided by, right, etc. square, right? That's we care, right? And but if in the case that we care about is whether they like spicy food, they don't like, they like, they don't like, right? You can also like is 1, don't like is 0, so on and so forth, right? In this case, mu, which is average, is just called pi, right? And this is pi or minus pi, right? And if we collect some sample there, right? Again, we will have x bar and s square, right? And in that case where we have sample, again, we have P, right? And this is P1 minus P, right? So that's the distinction, right? Pi is simply the population mean, right? But when you apply to CO1, right? Mu will be just pi, right? We care about whether people like spicy food, right? Average of the people like spicy food is exactly proportion of people like spicy food, right? Because plus 1, 0 over n, right? It's exact proportion, just a pi, right? So I hope this graph can kind of make sure that's clear. But that's, I think we have that pretty explicit, but I try to be, let me know if I'm not made clear enough, okay? I hope that's okay. If there's no further question, I just, any tips for the project? So I would recommend that you, of course, make your question as fun as possible. I mean, right? That is, pick up the right question and answer the right method, right? And do the right analysis, right? All of them are nonsense, but that is what it is. But the worst case, if you can't come up with anything nice, right? That can't do anything good, at least make it look good. Okay? As P school, packaging in the right way. I mean, even the same thing, tell the right story, put in the right perspective. It's very meaningful. Okay? Don't try to make it too wordy, right? Try to make it catch people's attention, right? And people read it and like it, and that's it, right? Because you are the introductory stat class. No one expect you to do a very complicated stat analysis, right? And just we want you to apply it and package and present it nice, right? Because many of you said this class is very difficult, which I agree if I were you, right? When I first learned statistics. And that's why I try to make sure that you apply it, then I know you know it, then that's important, right? Of course, the most important part is make it fun, right? Because our class is very boring, I can imagine, but try to pick up a topic that you are interested in, right? Asking how many people are being a Turkish or Argentina people when you apply to YouTube Premium, right? So that may be interesting question. Thank you. That's a good joke. I wish that the course can be taught in Chinese. I wish so, but that is one of the reasons why I come back to Chinese U. But the fact Chinese U, the B school, we are internationalized, so I have to speak in English. In the rare case, if you want to ask me question in private, I can talk in Chinese, no problem. Okay, but when I teach, we have to do in English. Of course, if you have particular reason that you want me to talk in Chinese in private, I can record that particular part, so that I can able to answer that. If you speak other language, I'm sorry, I can only speak. The maximum thing I can speak is English, Chinese, and Cantonese, and that's only the three language I know. Okay, I don't speak Vietnamese, Korean, Japanese, other. I'm sorry about that, but there's some limitation how many I can speak. But if you really ask me question, I'll try. Okay, I try. Let's see. Yeah, that's good. Everyone got it right, because yesterday I got it. Someone thought it's Monday, but luckily that everyone got it right. So always you can see in terms of opinion, right? We never have 100% for this weather. Okay, so it's always interesting, right? Because never I do this for this whole semester, I never have a consensus on this one. Okay, very interesting. I don't know, maybe someone would think about this as an interesting research question to think about. So the speed is okay. So far it's okay. Most likely you can follow most. Okay. And I do recommend you to, when you before you do your assignment, read the green box slide again. Okay. And before you do it, so you know what's going on there, right? And the green box is all matters, as I said, right? I mean, there are a lot of things I cover in the class, okay? Because otherwise, if I just give the formula, I train you how to apply, then you just become a machine and easily forget. So I hope I will try to tell you why they're true, okay? Way beyond what you need, okay? But I try to give you an idea why this formula in this way, so that you have some idea what's going on, right? It's easy just to apply the formula, right? With AI these days, and these days you just very easily apply things, but you don't know they're right or wrong, right? So probably you need to, that's why I want to teach those kind of stuff. Yeah, I'm very sleepy as well. Everybody very sleepy, same as last another section. I do agree that everyone's very sleepy, because I think it's towards the end of semester. Every energy exhaust. So you can see I'm trying to slow down a little bit. Okay. And I hope that's okay. And so now we have 7 C's, A, B, C, D, E, F. So which C will be where we are? Okay, let's see. So there's KFC. Okay, that's fun. So there are two person, the car collide each other. One get faint. Okay, the one who got faint is called Xiu Ming. So which one is still awake? So let's see. Okay, let's think. Okay, the other guy is called help. It's a good joke. Hopefully you don't got too sleepy by now with some joke. Do you think the skills we learn? Yes, for sure. Most of things we learn will be replaced as economists, but it takes time to get replaced. So we still have some marginal benefit to do, but at least now the thing is you need to read the table. Okay, in my days, the computer is not there yet that frequent, and you still without a computer, the calculator, the computer is very slow, right? And one of the reasons probably some of you may know, my undergrad is an actuarial science, right? And all the actuary is basically doing what Excel is doing, right? And when I worked as actuary intern like 10 years ago, then I noticed that everyone is basically doing Excel or the computer there, okay? I figure out that 30 years down the road, probably I will got unemployed or the market become very competitive. So I exit and I become a professor. And now I notice AI is there. So professor, the job will probably be gone in 10 or 20 years time. So I recommend my son never follow my path because basically probably is no point. Okay. And but same, I think that the analysis will be replaced. And probably in the old days, a lot of analysts is analyzing financial data, produce report. And if you look at Thomson Reuters terminal or other terminal, you see a lot of the data analysis report is generated automatically. So those jobs are gone. Or look at traders, right? One of the most rewarding job in financial industry, right? And actually they are replaced by no more finance and MBA people doing there. Now computer engineer do the job. Okay, I think I read the news like in New York, I think Goldman Sachs, what a big investment bank, they have 300 people doing the traders. Okay, and now they all replaced by 10 data scientists. Okay, so I mean, some data scientists will be got replaced, right? But as a data scientist, you replace some other people as well. Okay, so this what we call in economics is called creative destruction, right? Something is being destroyed and something is created. And then probably you don't know input Chinese, you learn the Changjie, right? And now probably not any of you know it, but when I was a high school student, actually I learned this, I type pretty fast, how to do it very fast. But now all those skills become obsolete, right? For sure, some of the skill you learn can be obsolete. Okay, so that's why in this class I focus on idea rather than formula, right? Because they easily calculate Excel, everything is being done quickly. So I tell you why they're true, and hopefully, at least this skill will still be useful. Okay, if in the case that we no longer need human to do anything, then probably everyone got retired. Okay, everyone is enjoying the sunshine, drinking things near the beach. Okay, so doesn't really matter anyway by that time. So don't worry about that. So when everything is replaced by AI, so we all replaced by AI anyway. So at that point, no difference, right? So everyone enjoying their good life near the beach. Okay, so but before that, I mean, let's be realistic. You still need to study data analysis. Okay, unfortunately, you still have the midterm. Sorry, no midterm. Have your assignment or thing to do. Okay. Okay. I hope I answered that. But the answer I gave is as an economist, not as a teacher for this class. Okay. So I hope that's okay. So what I want to talk about today is called hypothesis testing. And for those who do law, you will find this is the thing that is most useful, or that is very closely related to what you learn, or is the idea. Okay. So hypothesis testing is closely related to estimation. With an estimation, what we're doing is use the data, right? Remember the graph here? I think the graph is very useful. Okay. The graph here is we don't know mu, right? overreaching question last classes. We don't know mu, right? How we going to get mu? Right? We use this X bar, right? We use this guy to give an educated guess on mu. That was what we learned, right? We use a sample to guess what's going on in the data. Okay? So again, we do the same thing in this topic as hypothesizing. But now we are not simply guessing. We are going to see our knowledge on mu, which come from previous guess, right? Or come from someone who claimed it, okay? We try to see if this claim is supported by data or not. So the direction is kind of like reverse, okay? We have some knowledge on this, mu. We want to know the data we collect, which is X bar, is consistent with our knowledge on mu. Is that clear? Let me repeat the statement. What hypothesizing is, we have some statement, hypothesis, right? Some idea on what mu or sigma or other things should be, okay? We have some idea what they are, okay? Either in the accountant contest will be the client claim something, okay? You want to test it. Or in the law setup, you want to know, you are saying that guy in the UK system, right? The defendant is innocent, right? You want to prove whether it's guilty or not, right? As a prosecutor, right? And you look at the evidence, whether it's going to support the claim or not, right? Is that clear what we're doing? So using data to see if our assumption, our hypothesis, our knowledge on the population is right or wrong. Is that clear? So one example is like this, milk, right? And it is said 250 milliliter, milliliter, right? And if you are consumer counsel, you want to see whether it is actually 250, right? Or a claim is low sugar, right? You want to actually test it's actually low sugar or not, right? This is the question actually is, or you are the quality control, you need to test, right? And probably you know the quality control of the recent iPhone is not very well, right? So that is related to this topic, okay? So let me go step slowly because in this one, you see the idea is very complicated. The formula is very simple. So go back to this graph. Basically, we tell you most of the calculation idea behind. So you can imagine we learned from the last class, right? How you can say whether support this idea on mu or not. The overreaching idea, roughly, is based on our idea of hypothesis testing, interval estimate, right? We learned that X bar plus minus this guy, suppose we know sigma, right? Will very likely include mu, right? Remember this, right? This is what we have been saying. X bar plus minus something is our guess. And we say this guess will very likely include mu. So that gives us the way to do hypothesizing. If you say mu, in this case, 250 in the drink. If you do data, collect many boxes of the same product, you calculate the sample mean, calculate the interval. If the interval include 250, then your data is consistent with the claim. If you construct the interval does not include 250, then your data doesn't support it. That's the idea. Is that clear? It's very simple, right? Because it's simply asking our interval estimate, is it including the knowledge? We know. If not, hey, the data is not supporting. If so, the data is still consistent. We don't reject it. Okay, so that's the overreaching idea. Of course, there's some technicality here, but this is the overreaching thing. You basically get most of the thing. Okay, but there's a lot of technicality here, but the overreaching is very simple, right? Interval estimate, whether the interval we included. Okay, but we'll go into a little bit more detail because we do require some further detail to get a better estimate, right? Because if that's so simple, then we're done. We don't need to. You can see we have 100-something pages for this one. Okay. Oh, by the way, some people ask me the R studio thing. The R programming, the optional tutorial will be at during the makeup period. So it's December. Will be December. I will put it there. So be in December 5th, 4 and 5 in the B.B.A lab. There. So it's after your final test. The final test is in 1st of December. Okay, but this is optional, so you might or may not to come. Okay. So I put that on later. Okay. So hypothesis testing. Okay. One sample. Okay. I will go slowly on the one sample. Okay. And two samples will be very similar. So I will be very fast. Okay. Because very similar things just apply different formula under different contexts. So I'll be very quick there. But I will be very slow in the one sample because they form the foundation what we are doing. Okay. And once we learn estimation and hypothesis testing, basically you learn all the way you do statistics. Because all the statistics we learn here in other classes is basically we have different assumptions, give you different model, give different technique to do estimation, different way to do hypothesis testing, and that's it. That is all the model is about. Okay, so that's why I have to be very slow here. Otherwise, if you don't get the abstract idea, then it's very hard to extend the knowledge we learn. So hypothesis testing, the idea, as I said, is you look at the sample. If the sample is going to support what we know about the population, okay? Use a small picture to test whether our knowledge on the big picture is consistent or not, okay? And the idea is we have a working hypothesis or working claim. We will assume the claim is true, okay? That is starting point analysis. We will work from that, okay? And we will reject the null if not support, okay? So it's kind of biased towards the null, right? We only reject if not support. Same as the system in the UK system. Probably people who do law would know, right? In the UK system or the common law system, you assume the defendant innocent until proven guilty, right? And I subsume the case in, probably people will correct me if I'm wrong, the law system in China is different, right? You would be assumed guilty until you're proven innocent, right? And they're asymmetric, right? So whether you have a working claim or otherwise, we're different. So that's why in statistics, there have the way two important thing is called null hypothesis or alternative hypothesis. Null is the one that we will maintain, we'll keep it, okay? We want to reject it, but this is what we maintain, okay? And this reflects what we know, okay? And we call H null or H naught, okay? And the alternative is the one that we are going to see the data is going to go into this direction, okay? If we call H1, okay? And do remind you that they're asymmetric, okay? you cannot swap them. They're different things. Okay, you cannot simply swap them because all the time we assume our null is true. Okay, we will analyze whether null is true and see whether things are violated. Okay, is that okay? Okay. So this is the formal definition of hypothesis testing. Hypothesis testing is basically a rule. Later you will see. We specify when we will accept or not rejecting, or will reject. Okay. So it's based on data. The data, based on data, will tell us whether you accept or reject. Okay. So this is a formal definition. This doesn't make too much sense here, but after we go over everything, come back to this slide and you will see. So a lot of thing here is a little bit framework, so probably doesn't make too much sense here. We just define it. Okay. Later you will see. We just define hypothesis is a rule that based on sample value, you accept or reject. Okay. The simplest idea is like this. Okay. In a court, in a murder case, right? Suppose you are trying to say a guy is a murderer. Okay. But if the murder happened in Hong Kong, okay? Suppose the guy is actually physically in US, okay? Then he can't really get it, right? So you would define these are valid evidence, right? To prove you're innocent, right? So these are known case. That's the idea. It's hypothesis, right? We'll give a rule telling you that what are the sample value that you will reject or not. Okay, it will become more clear soon. Okay, but that is the definition. But before we do that, let's talk about a further detail or further restriction of what we're talking about, because hypothesis testing can be very big. We focus on very small cases that we can analyze. Is we have first to distinguish two things. One is called simple, or the alternate composite. Simple is just I conjecture the population mean is 3, just one value. If I have more than one value, that's called composite. Okay, it's combining multiple. Say more than 3, less than 3, not equal to 3 are all composite. Okay, and this is the distinction, right? Whether simple or not simple. Okay. The next is the restriction in our class, okay? And not in our class, but all the introductory class. That's what is being said is always focus on the null is simple, okay? The null we know is simple. And alternative is always composite, okay? And if you are to relax that, that is way beyond undergraduate, okay? Usually covering the master and PhD level. So since we're undergrad, right? We do what undergrad do. So this is what it is, okay? We assume our null is always positive. So we say mu is equal to some number, okay? In this case, mu is 250. And alternative will be, what we focus on is one of the 3. Less than, more than, not equal to. Okay, I will tell you when to use what, okay, in a second. Okay, so in the composite, we can further decompose it in 2 parts. The other is called one-sided or two-sided. Okay, if it is less than, it's one-sided, or more than one-sided. If not equal to, actually means more than or less than. Okay, I'll give you more detail now. Okay, so when you use which one? Okay, so let me be very precise on when to use what. Consider the case you are consumer counsel. Okay, you want to make sure that in the package it said 250, right? If 251, are you going to complain?
If you turn out to be 260, you don't complain, right? More than is not a problem. Only problem, you take action is less than, right? So in that case, the alternative will be less than. Okay? And remember it said it's low sugar, right? If say low sugar actually means, I don't know, maybe one gram, I forget, I don't know what is criteria, but it's low sugar. There's some range, okay? If turnout is too little, are you going to say anything? No, right? But if too much, you're going to jump up, right? And say, no, that's something. Then use more than. Okay. And when you be equal, not equal to, when you use it, is when the case that you would take action, you worry about if it's not exactly equal. When, if you're auditor, you're going to say inventory how many there, right? And if it's not the same as told by the client, regardless it's more than or less than, you're not very happy. You take action, right? There's consequence. Then you use not equal to. Okay, so that is what I said here, right? If product control harmful substance is more than main ingredient, less than, you will not be very happy, right? So let me give you a further example. I think this is an interesting one. Okay, consider you are a local club, okay, owner, okay, and now we have agent society, right? You're thinking about whether the mean customer is more than 45, right? Why? Because maybe the pub has been showing K-pop song or J-pop songs, right? Now you imagine that all the young people go to Shenzhen, right? Now what is left is old people. So what you're going to do, maybe you should take away all the K-pop thing, replace it by TVB shows, right? That's all people watch, right? Then is it going to be the case? Okay, so you would only worry about if the sample mean is less than 45. Oh, sorry, more than 45, right? So you will take action more than 45. This is what you care, right? If less than 45, you still do the K-pop show there, right? You still ask the pub, still asking some young people to perform, right? If it's too old, then you would ask very old people performing, right? You would ask the TVB old star to do it, right? And if usually if you don't have any knowledge about it, okay, or consequence is important, whether they're accurate or not, okay, like this, okay. A firm claim the revenue is 3,000, right? You don't want overstatement and understatement, right? Because they are misstatement, right? So if it is not 3,000, then you're not very happy, right? You don't want them to overstay, which might be a problem of inflating their financial statement, right? Investor may sue you, bank may sue you. If understatement, there may be a tax evasion, government may sue you, right? So you don't really want understay or overstay, right? As an auditor, so you want to make sure that it's the same, right? Because the liability to you as both, right? I mean, of course, if for you as a bank, you care about is less than, right? If government, the tax maybe care about more than, right? But if auditor, you care about both sides. Okay. So one of the key here. Oh, did I go over it? Oh, still okay. The key here is called the test statistics. Okay, is in the hypothesis testing, we will calculate the interval. Okay, and for hypothesis testing, the key here is beside defining null hypothesis, alternative hypothesis, you define them, and based on them, you define one thing that's a key for this class, or sorry, for the rest of the other class as well, is called test statistics. Okay, this is a statistics that we make decision. Okay, and it's a random variable, and based on the null hypothesis, we will create what we call critical value. Okay, the critical value is the value that if whether is what we call the reasonable doubt idea. Okay, whether beyond that or below that, we will make a different decision. Okay, probably point of no return, you can say, right? Let's give the idea. Okay, I'll talk about more detail later, but I give you the idea how we do statistics. Okay, the idea is that this. Okay, we want to test whether mu is the first case, right? Whether mu is bigger than this, bigger than A. Okay, you can imagine A is 250, right? Maybe you want to see whether the box of this is more than 450. Why? Because maybe the company don't want to put in more liquid inside because otherwise they lose money, right? They want exactly 25. Okay, this is your quality control. You don't want more than 250. Okay, so how you're going to do this? Okay, one way to think about this is X bar is a test statistics, right? And how you do it is collect data with sample mean there. If this sample mean is very large, okay, then you reject, right? Suppose you get the data is 300, right? Then probably you would be not happy, right? You would say no, right? If you get is 200, then you don't worry, right? And the question is likely that how large is large, right? I just give final statement here, how large is large. The thing is, we know this, assume x0, mu is 250, right? That's what I assume. We'll finish this and then we'll go. So this is here, right? And the question is, how large is large? Okay, and we have to make decision here, but usually what we said is this value we call critical value, means if this is large enough, then we reject. Then how do we say this is large enough? How do we measure this, right? How is there an educated way to say this is large? Very simple. We'll say this area is small. Okay, usually 5%. Okay, the smaller this area, the further this away, right? If this is small enough, right, then this is far away. Why? That means that the probability for this or more is so small that you would think the alternative hypothesis is correct rather than null. So that is the overreaching idea. Of course, we go to more detail, we find this, but this is what it says, right? Is if we say the x1 is big, how big is so big that we would take x1 rather x0? Is this area is very small. Okay, how small? 5%, and this is called the critical value, right? That is beyond the reasonable doubt that was going on. Is that clear? Don't worry about that. We'll go over again this. It should be no problem. So make sure that next Wednesday we have no class, but next Friday we have class. Okay. So makeup class will be in the December 4th and 5th, right? If you attend, you attend just fine. Okay. I see you next Friday.